Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all to lecture number 11 on the subject of computer organization and assembly language programming. The title of today's session is Design of Registers. Well, today we will start with a quick recap of the sequential circuits, which we talked about in the previous session. We'll talk about the concept of CPU registers. Then we will design and write HDL code for single bit as well as 16-bit register using the built-in D flip-flop chip. And finally, we will verify the behavior of our designed chips by loading and running them in the hardware simulator. So let's start playing. Well, this slide gives a quick recap of sequential circuits that we discussed in detail in the last session. And the output of a sequential circuit or the state of a sequential circuit at time t depends on the current input and the stored state, which of course depend on the input at time t minus 1. And there are different types of flip-flops that we talked about in the previous session, but for designing all the sequential chips like registers, counters, RAM and so on, we will be using the simplest and the most elementary sequential chip called the D flip-flop. And the D flip-flop just maintain a state, that is, it just stores a single bit of input from the previous time unit. Well, the way our hardware simulator provides us a built-in NAND gate chip from which we have designed all the combinational circuits so far. Similarly, our hardware simulator also provides us with a built-in DFF chip from which we will be designing all the registers, counters and memories of the hack computer. And this is what we are going to start with in today's session. Let us talk about the CPU registers first. Well, dear students, as you all know, a register is a small memory place inside the CPU that may hold data, memory address, or maybe an instruction. The size of registers in a 64-bit computer must be of 64 bits. Sorry for these typos. In our hack computer, since it is a 16-bit computer, so the registers we are going to design will also be of 16 bits. And there are several different classes of CPU registers which works in coordination with the computer memory to run operations efficiently, and we will talk about this in the future sessions. Excuse me. And let us start with the design of a single bit register. Well, a single bit register, which we call a bit or binary cell, is designed to store a single bit of information. Please remind me later. A single bit of information, a 0 or a 1. The chip interface shows that it has two inputs, a single bit in and a single bit load, and a single bit output. The input pin carries the data bit, and the load pin enables the cell for writes, and an output pin emits the current state of this binary cell. When you read the output pin of the binary cell, you will always get whatever is the state of the binary cell, that is, whatever is stored inside this bit. And to write a binary cell, we set the load bit to 1, and now whatever is there on the input bit will be stored inside this binary cell and will be available on the out pin in the next clock cycle. And when the load bit is 0, the chip keeps remembering the last input that was loaded into it for infinite time until a new load operation is performed. Well, this slide shows the chip interface and the function which this 1-bit register is going to perform. You can see the chip name is bit, and of course the file name is bit.htl. The chip interface shows that this chip has the two inputs, namely in and load, and one output, namely out. And the goal of this chip is to remember or store an input bit until it is instructed to load and store another bit. Let us try to understand how this chip achieves this functionality by an illustration on the next slide. Well, dear students, in this timing diagram, the time progresses from left to right. Time unit 1, time unit 2, 3, 4, 5, and so on. And these are the timing signals of the load and the in inputs to the binary cell. And this is the output which we are going to draw, keeping in view of this chip behavior. So let's try to do and understand this. Well, at time unit 1, if we try to read this out, we cannot determine the values as we do not know the history. That is, we do not know the state of the bit register at time 0. At time 0, we do not know the state, so we will not be able to determine what the output is. So let us put a gray over here. Uh, uh, Moreover, keep in mind that at time unit 1, since the load is high, uh, and this in input is 1, so this 1 is stored inside the bit register, thus making the state of the bit register to 1. At time 2, the out will be the previously stored state, and since the load input is low over here, so the state of the bit register will not change. So the out will be whatever is there in the bit in the previous time unit, and this makes sense. Well, at time unit 3, the out will be the previously stored state, and the previously stored state is of course 1. And since the load input at time unit 3 is 0, so the state of the bit register will not change. Okay, so this also makes sense. Let us move on to the time unit 4. The out will be the previously stored state, and it is 1, as shown. However, remember that since at time unit 4 the load input is high and the in input is 0, so the state of the bit register will change to 0 at time unit 4. Let me repeat, since at time unit 4 the load input is high, so the bit register will be written by whatever is there on the in input, and that is 0. So at time 4 the state of the bit is 0 now. So let us move on to the time unit 5. The out will be the previously stored state, which is of course 0. Great. Moreover, since at time unit 5, since the load input is low, so nothing is written or loaded inside the bit register. Well, dear students, the critical time unit is 4. We want to load a value 0 at time 4 in this bit cell, and for that we have made the load input high, and in the in input we have placed a 0, but this will only affect the output at time 5. My dear students, this is a very important and a bit tricky concept. I strongly recommend that you go through the simulation again, this part of the simulation at least, to have a clear understanding as to how reading and writing are done in this single bit register. And let us now try to implement this 1-bit register using a D flip-flop. We have discussed in the previous session as well, the behavior of D flip-flop is that whatever is there on the input is stored inside the flip-flop, and if we do not want to load a new value in this flip-flop, rather want that whatever is the current state of the flip-flop, it remains same for all the clock cycles. Uh, so what to do? We take the output, that is the current state of the flip-flop, from here and plug it back to the input of the D flip-flop. So this way, this D flip-flop will just keep on having the same value in our loop until we tell it to load a new value from this place. The problem is uh, the D flip-flop of course has only one input, but at times we will like it to maintain its current state. That is, we will like that the input should be this one. and at some other specific time we will like to have this D flip-flop to load a new value, that is whatever is there on this input in. So how to do that? Of course, this design will not work. So one possible solution is using a multiplexer. So this is the final design of a 1-bit register using D flip-flop. There are two sources of input to the D flip-flop, as you can see. One input is the output from the previously stored state, and the other is the new input. And which one of these two inputs we want to plug in the flip-flop depends on the load input of this 2 by 1 mux. Let us understand this using this timing diagram. Well, we have the time over here, the load input, timing signals, the in and out. Well, at time unit 1, the load is 1, the in is also 1, but we do not know the previous state of the flip-flop. However, since the in is 1 and load is 1, so the new input is stored inside the D flip-flop is 1, uh, which will be available on the next time signal 2. But over here we cannot determine what will be there on the out. At time unit 2, over here everything is clear. Well, at time unit 2, you can check out that the load is 0. The load is 0 as shown over here. The in is also 0. The in is also 0. And the state of the flip-flop, previous state of the flip-flop is 1, which is coming up over here. Since the load input is 0, so the mux will send this 1 over here. And the previous state of the flip-flop is maintained. Let me move on to the 3. At time unit 3, the load is 0 and the in is also 0. The load is 0 and the in is also 0, and we know the state of the flip-flop is 1. So since the load is 0, so this 1 is placed over here and this 1 goes in. At time 4, we have the load as 1 and the in as 0. Load is 1 and the in is 0. The previous state is of course 1, that is coming here. Since the load is 1, so the multiplexer will output this input to the D flip-flop, that is 0 will come over here. So this 0 will move into the D flip-flop, the state, and here it goes. So this is the basic implementation of a single bit register. My dear students, if you have understood this, I think you should be able to easily understand this HTL for the 1-bit register. The name of the chip is bit. The chip interface shows that it has two single bit inputs, namely in and load, and a single bit output, namely out. The chip implementation shows that we have used two helper chips, a 2 by 1 multiplexer chip that we have designed in a previous session, and the built-in D flip-flop chip. And I think the connectivity is quite clear to you, and this code makes sense. Okay, so let us move on to our hardware simulator and see a demo of this 1-bit register. Let me move on to the terminal, and here we have our hardware simulator already running. Let me load the chip. And the chip I want to load is bit.htl, which we have just written. You can see here is the code of the chip. The input pins of the chip are in and load, and the output pin is out. Note over here the name of the chip is bit, and in the brackets you can see clocked over here. So this chip is clocked, that is, it contains the built-in chip DFF, which itself is clocked, and due to this you can also observe the clock icon on this taskbar of the hardware simulator, which is enabled now. And this clock is basically used to simulate the progression of time in the simulator, or we can say that it is used to simulate the clock pulses or clock cycles. And beneath this clock icon you can see the time, which is 0 right now, which will get incremented each time I will click this clock. Let me do that. Let me do a tick and a talk. a tick and a talk, a tick and a talk. So you can observe after a tick and a talk, we move from 3 to time 4. Also, I'm progressing the clock manually, and of course, I can also write test script that includes command like while true do tick tock that will cause the clock to tick and talk forever. But for now, we are going to do this manually. And before I load some value in the single bit register, let us reset the clock. Let me reset this clock by clicking this button. This clock will be reset. Okay, that's great. And let me write a 1 in this register, and to write a 1 I need to place a 1 in the input, and I need to make the load high. So I do a tick, nothing happens over here, and I do a talk, and now the single bit register contains 1. So that is great. Let me keep doing tick tock. And remember, every time a new value at this in is loaded inside this in this single bit register, and the value is 1. So whenever I do a tick tock, the value of 1 is added over here because the load is high. Let me make the load 0, and remember, now whenever I do a tick tock, nothing is loaded, and to prove that, let me place a 0 over here. And now if I do a tick tock, this 0 will not go inside. This 0 is not going inside inside the single bit register. However, if I made this load to 1, and then I will do a tick and a talk, you see the value at in has been stored inside the D flip-flop. So that is great. I think the concept is clear. So let us fall back to the slides. So now we know how to design a single bit register. Let's try designing a multi-bit register as well. So dear students, register is actually a group of flip-flops. So this is a multi-bit registers having multiple these bit cells. Each bit is capable of storing 1 bit of information. N-bit register consists of a group of n flip-flops. So if we have a 16-bit register, there will be 16 flip-flops or 16 binary cells capable of storing 16 bits of information. And so this is a block diagram of a 16-bit register. And this is the clock, and 16 bits of a number coming in will be stored or written inside the register only if the load is high. And whenever we probe this in output pins, we will get whatever is there inside the register. So this is the overall concept of a register, and the API of a 16-bit register chip is actually the same as the 1-bit register, except that the input and output pins are designed to handle the multi-bit values. The interface of a 16-bit chip is shown over here. The name of the chip is register. The inputs are in and load. In is a 16-bit value, load is a single bit value, and the output is again 16. And the behavior is, if the load is high, the new values are stored. Otherwise, whatever is there in the register will be placed on the output. So let me read this para for exact understanding of the read-write behavior of this 16-bit register. To read the contents of a register, we simply probe its output. So whenever you want to read the register, you just read these 16 pins. So whatever is there inside the register, you will get it over here. However, to write a new data value into a register, if you want to write a new value into this register, we put the value at the in input, and we set the load input to high or 1. And in the next clock cycle, remember, in the next clock cycle, the register commits to the new data value, and its output starts emitting the new data value, that is D. And it will keep emitting this new data value forever till the time we decide to write another new value inside it. So, dear students, this is a slide that shows the HDL for a 16-bit register using the already built bit register. See the interface. The in has 2 inputs, 16-bit in and a single bit load, and the out is again a 16-bit output. There is a single 16-bit output And over here in the implementation part, you can observe that we have used 16 single bit registers. And the first, this bit register, the input is the least significant bit of this 16-bit input, and if the load is 1, the output, that is the state of this bit, will be changed to whatever is there on the least significant bit of this input. So we have 16 uh, uh, single bit chip over here, and using these 16 bits, we have used this 16-bit register. And let me move to the simulator again to verify the behavior and the code that we have written for this 16-bit register. Let me load the chip first. So we have the code over here. You can see this is the code. Fine. Let me set into, let's suppose, 1 to 9, and do a tick tock. Nothing happens. This is because the load is 0. Let us set load to 1 and do a tick and a talk, and you see the register now contains 1 to 9 in binary. The register contains 1 to 9. These are the 16 bits that contains 1 to 9 in decimal. Let me set load to 0 now, and let me try to read the contents. We can always read the contents by doing a tick and a talk. Every time we are getting 1 to 9, let me change the into, let's suppose, 100, and do a tick and a talk. Nothing happens. This is because the load is still 0. Let me set the load to 1 as well. Now this register will be written. Let me do a tick and a talk. So it is 100. That is great. Let's fall back to slides again. Okay, dear students, that is all for today's session. Please practice writing the HDL of the register chips and verify the behavior by loading and running them on the hardware simulator. You can download the HDL, the test scripts, and the compare files of the chips discussed today from the course repository. I also recommend that you should practice different timing diagrams that we have used to describe the behavior of D flip-flop and the single bit register on a piece of paper by yourself. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.